Okay, so now we've talked about our definitions and the fundamentals. Now we're going to talk about ways to calculate settlement. And I'm putting I'd like to divide the settlement methods into two different ways of doing it. And this now deviates from the way that the settlement is described in your textbook. But I think it's important to think about two different kinds of settlement, or two different ways of calculating settlement. One are modulus-based methods, and that's what we're going to talk about first. Modulus-based methods, and the other one, for the shorthand, I'm just going to call E log P methods. And this relates to the discussion we had earlier about stress-strain models for soil. Right? We talked earlier that if we've traditionally always plotted stress-strain for soils in terms of E log P, but we found that that's not always the most instructive way to look at the stress-strain behavior, that sometimes, if we look at it in linear space, it's actually quite linear. And so there's two different approaches to this, and all the approaches that use a arithmetic plot of stress versus strain, I'm going to call modulus-based methods, and then we'll talk about the E log P methods in the next section. So that's my distinction, and I think this is, you will find in all literature and textbooks, you will find people that present all, I'm not going to show you any new methods. I have not dreamed up any new methods for computing settlement. What I have done is put them in these categories, which I do think is new and unique. I don't hear other people talking about them in these ways, because I found myself very confusing the different methods of doing this and how they related to one another, and I find it very helpful to think about them in terms of methods that are based on modulus, which is based on a linear plot of the stress-strain curve, an arithmetic plot of the stress-strain curve. I didn't say it was a linear function, but an arithmetic plot of the stress-strain curve, where we're going to calculate, we're going to evaluate compressibility based on a modulus, versus the E log P method, where we're going to evaluate compressibility based on a compression index. So one of them is going to be the slope of the semi-log curve, and the other one's the slope of the arithmetic curve. Not necessarily linear in either case. Okay? So we're going to start with the modulus-based methods. So what are these learning objectives? Well, these learning objectives are for you to compute. We're going to first start with some elastic methods. Remember, we talked about elastic methods when we were talking about stress distribution. Now we're going to talk about elastic methods for computing settlement. And then there's several models of this I would like you to be able to use. One thing that you need to be able to do is to be able to understand how to interpret plate load tests, because this is a bad method for estimating settlements that's used by many, many people. And then there's two aspects of the elastic-based methods which you should be able to do. One is those based on a uniform material, and then this methods that are based on Mayne and Poulos' material. We'll talk about that. And then I would like you to be able to use Schmertmann's method. So I want you to not only be able to use Schmertmann's method, which is this second learning objective, but I also want you to be able to describe theoretically where it comes from. I think it's really important. I think the vast majority of the people that use Schmertmann's method have no idea where it came from, and doesn't know what it applies, doesn't know how it's derived, and therefore oftentimes misuse it. And then finally, I'd like you to be able to use what I call the incremental constrained modulus method. This is a total kitschism, but I was looking for a title for this. And this is actually the method that Schmertmann now thinks is the best method for computing settlements for sandy materials. So Schmertmann actually even no longer advocates his method. Well, no longer advocates it as the best method. And we'll talk about the pros and cons of that. So though I expect you to do all those things. All right. So let's go back to elastic solutions. Okay, we're gonna look at elastic solutions, and we're gonna look at real behavior and see how we can make the two fit together. So let's assume I have a circular loaded area. It's got a half width of small b. So we can look up the elastic solution for the displacement of a circularly loaded area as a function of S. It won't be the same under every place in there. And we're going to find that it's Q, which is the applied stress, times 1 minus nu squared over E, those are elastic constants, right? Times the footing width. And then he's got a couple of ratios in here that he's written this out as a dimensional and stuff. So Z over B is the relative depth below the footing. Okay, so this is a settlement at the center. And then he's got this other ratio that's based on the Poisson's ratio. And I5 and I6 are influence factors. So I5 is a function of Z over B and S over B. So it's a function, I5 is a function of the relative location you are below the footing, in both directions, right? And I6 is also a function of Z over B and S over B. It's just a different function. So if we look at this is just the elastic solution. So we have a uniform, isotropic, homogeneous, elastic material. We find that the settlement is a function of what? It's directly proportional to the width of the footing. It's directly proportional to the load. It's a function of the elastic constants, and it's a function of where you are, under the footing to the side. That all make sense so far? Okay. Well, when Z is 0 and S is 0, where am I? Right under the middle of the footing. So let's just deal with that, because that's actually usually what we do in these cases. We just calculate what's going on in the middle of the footing. Oh, that's good. So let's do that. So when S is 0 and Z is 0, I5 is equal to 1 and I6 is equal to 2. So now what does my equation become? Well, now my equations essentially become SE is equal to 2QB 1 minus nu squared over E. Right? With me? I'm now just calculating the settlement right under the sitting of this circular loaded area. Or if I wanted to, I could just write that as SE is equal to some other influence factor times B times Q over E. And that influence factor is just a function of the stiffness of the material, and the geometry. So, and Holtz and Kovacs gives you this equation. They left nu in it. You can leave nu in the equation or take it out. So theirs is just a different stiffness factor. Okay, so what does this say about the settlement? The settlement under the center of a circular loaded area. Well, it's directly proportional to B. It's directly proportional to Q. It's inversely proportional to the modulus. And you got to multiply by 1 minus nu squared and times some I sub S, which is an influence factor that has to do with the relative stiffness of the footing and the location where you are relative to the center of the footing. So that's both a shape factor and a rigidity factor. And you can look those solutions up. Okay, so let's think about this for a minute. So here's my footing. This is the plate load. This is kind of the plate load test, all right? So I'm going to do a plate load test. I have a footing that's B0 wide. I'm going to put Q on it, and it's going to settle some amount. It's going to settle some amount S0. And then I'm going to put a new footing out there that's wider than that. Okay? I'm going to put the same Q on it. It's got the same Q, which means it's got a larger load, right? Load's higher, but the stress is the same. And is it going to settle the same? It's going to settle more, right? And if we put another one that's even larger, it's going to settle even more. So what did our elastic equation tell us? If we have a homogeneous isotropic material that has E, constant versus depth, that was the equation we just looked at, what does it say our relationship is between the footing width and the settlement for a constant applied stress? Do you remember? So it was directly proportional, right? Here it is. SE was equal to some I times B times Q over E, or if you want to put Poisson's ratio in there, that's fine. So if I start off with, I'm going to do this as a relative sense. I'm going to put B over B0. Our elastic equations tells us if we keep increasing the size of our footing, we're just going to get more and more settlement. It's a linear function. So if I'm going to do a plate load test, I can do a plate load test, and I can do a teeny little plate load test. 1 foot square, that's what we usually do, right? 1 foot square load, right? I can calculate a settlement. I can give you the settlement any size footing you want. All you got to do is multiply by B, take the settlement I got for that 1 square foot plate, multiply by B, and I got the answer. Is that what happens? No. What happens if I keep increasing the width of the footing? What happens in reality is this is what we see. If you do this, if you go out in the field and you do this, you get a bunch of different plates, start with a small one, keep it bigger. It'll start to increase with B. You'll initially get an increase with B, but eventually the increase will get less and less and less, and eventually it'll kind of flatten out. Why does that happen? Here's my elastic model. It told us it should be proportional to B. So why does that happen? Yeah, well, modulus isn't constant with depth, right? There's a lot of reasons that doesn't happen. Modulus isn't constant with depth. The material's not elastic material anyway.
Increasing the 2D, but it's in 3D. So it's 3D. That's why.
Well, it could be there's three-dimensional effects. In other words, one part of your area is covered by a different material. Yeah, it could be that. Sure. This is a bunch of data that was plotted originally by Dilatometer in 1970. This was originally looked at by Terzaghi and Peck, but this is a plot of plate load tests. And you can see the general trend that it's not linear and that it curves off to the right. This is the original, there have been empirical fits to this. This is Terzaghi and Peck's original fit, and it's in, some of you have probably seen this. Have you seen this? This is in Peck, Hansen, and Thornborn, and a lot of other stuff. And all Terzaghi and Peck did in 1948, they just looked at these data and they fit it to this line. This is all empirical stuff. That the settlement that you're going to get compared to the settlement of a 1 square foot plate load test is 2b over b plus 1 squared. All they did was fit those data. Bajram and Eggstead said, well, that's not very good. And a decade and a half later, they gave you upper and lower bounds. They gave you a median there that you see as a dashed line, and they said, well, these are the upper low end bounds because they had a lot more data. That's still completely empirical. What's really going on? Well, if I do another elastic solution, but instead of having a constant stress, a constant modulus, if I have a modulus that starts off at 0 and increases linearly with depth, I'm going to get this solution. This is Gibson did the solution, and this is going to be my solution. The settlement's going to be equal to another shape factor times Q over KE, where KE is the slope of that curve. So what does that say the settlement is as I change the size of my footing? If I increase B, what happens to my settlement with this model? Nothing, right? This one says, this is what happens. That's actually pretty nice. What's nice about those two theoretical solutions, the one for homogeneous isotropic with a constant E and one for E that's linear increasing from 0? Yeah, our real answer is in between the two. That's always a good sign in engineering. It's like, hey, I got two theoretical solutions that bound the problem. That's always a good thing. That always makes us feel good. So I just need something that's in between there. Well, what model would be in between a constant modulus versus depth and a modulus that starts at 0 and increases with depth? How about a model that starts at a constant modulus and increases linearly with depth? And if we solve this model, if we look at this one, this is a paper I used to have people read, but I don't have them read anymore because they complained. Carey and Christian solved this model for us. And this one, it's not quite as simple as the other ones, but now your settlement's a function of E over K E sub B. This is known as the Gibson modulus. It's a modified modulus. And if you do the units on that, you'll find out that that's so K is the slope and E over B. So you find out it's got some funky units. But if you do that, it depends on the relative. It depends on the ratio, on this ratio. So these can all change. But if E over KE is equal to 0, then I have the case where E is equal to 0 and I have the white solution. If E over KE is infinity, then I have the case where I've got E is constant and I'm going to have the settlement as a function, is just a linear function of B. And if I vary the ratio of E0 and KE, I can get a whole bunch of different curves that fit in between the two of those, depending on what the initial modulus is and how quickly it increases with depth. So this is one way to solve the problem, which is to say, well, let's use a model where it's not a constant modulus versus depth, but it starts out of a constant modulus and increases linearly. And what's the only problem with this model? Well, yeah, I could find one that fits it, yeah. And so it doesn't capture the behavior perfectly. That's right. It as you get to E over K ratios that are higher, it gets closer to the uniform one, right? But now I have to evaluate not only E0, but I got to evaluate the rate of increase with E. So that's the other problem with it, and it still doesn't fit it perfectly.
Is it not dependent upon stress? No, it is.
Yeah, it's also a function of the stress. Yeah. These plots are all for a constant stress. Yeah, they're all linear functions of the stress. Everything else is saying you change the stress, you're gonna get it, right? Okay. So before we're gonna answer that question a little bit. Before we do that, I want to take a quick stop by and talk about the horizontal distribution of stress and displacement. So, you did this solution. This was 2 homeworks ago or something, right? If you apply stress to the surface, it gets distributed out laterally as you go down. So your stress at the top, which was a step function, as you go down, it gets distributed out laterally. If you go down deeper, the stress buildup is going to be farther out, but the total value is going to be lower. And you guys did this exercise not for a circular one, but for an infinitely long one, right? So this assumes that the applied stress at the surface is constant. And another way to say that, this assumes that we have a flexible foundation. So when do we have flexible foundations? Well, a flexible foundation, if we're just talking about settlement, could be an embankment, right? That's pretty flexible. It usually, like a steel tank is another classic one we use, because steel tanks, even if they have a 1-inch thick steel plate, if it's 50 feet wide, 1 inch of steel and over 50 feet is very flexible. And whatever load is applied in there is going to be distributed as a uniform stress across it. Think of a steel tank full of water. No matter what the settlement is, you're going to have the same height of water above everything, so the stress is constant. That's not the only thing that happens. Foundations have rigidity. Most foundations are not infinitely flexible. And the contact stresses that are generated under foundations are going to be a function of both the settlement profile, both the type of soil that's being loaded and the relative rigidity of the soil. So these figures come straight out of Holtz and Kovacs. If I have a flexible foundation, okay, so this first plot is just of Q, the applied surface stress, Q0. If I have a flexible foundation, no matter what kind of material I am, I by definition have a constant stress applied to the surface. Right, so the stress is constant. If we observe what happens in clays, let's start with clays. If we observe what happens in clays, we observe that we get more settlement, and we can actually measure this on things like tank settlement stuff. We actually find more settlement in the middle than we do on the edges. Well, why are we getting more settlement in the middle than on the edges for a flexible foundation? Well, let's just go back to this picture. If I plotted, I asked you to do this too. If I asked you to plot delta sigma v as a function of depth under the center of the footing, right underneath the base of the footing, what would the change in vertical stress be? Right under Q, what would be the change in vertical stress? Be Q, right? So right at the ground surface, it's going to start off at Q0 or Q, Q0. And what's going to happen as we go down in depth? It's going to decrease, right? If I ask you to plot that same function right out here at the edge, all right, we'll plot this direction just to keep ourselves. Let's see, this was Q to there, so this would be about Q0. Let's just do it right, just barely underneath the edge. It's still going to start off at Q0 right underneath the edge, right? But how's that going to change? So it's going to start off right there. What's going to happen as a function of depth? Are we going to have the same change? Are we going to have the same change in vertical stress as a function of depth over here? No, it's going to drop very quickly, right? Notice that this depth right here, that this is the change in vertical stress there, and there's a change in vertical stress there. Or another way you want to say it is that the change in stress is going to penetrate further in the middle than out at the edges, right? So why am I getting more settlement then? Why am I getting more settlement for my clay under the center than I am at the edges? Well, there's more change in stress under the center. I've got to integrate the change in stress as a function of the depth, right? And there's more load in the center than there is in the edges. And the contact stress right immediately under the footing is going to be constant. It has to be by definition. Well, if we observe what happens in sands, we actually observe the opposite behavior in sands. In sands, we observe that there's actually more settlement at the edges than the middle. Well, we have the same distribution of stress. What's the only way we can get more settlement at the edges than in the middle if we have the same stress distribution we have in clays? You've got less stress at the edges than you do in the middle. So how can you get more settlement in a location where you got less stress? Well, it's a result of the confining stress, but what's the material property that's changing? What's the only way I can take two samples of material, put a stress of X on this, a stress of 0.5X on this, and get more deformation than the one that's got 0.5X than X? What's the material property that's different between those two samples? Not Poisson's ratio, but the modulus, right? In sands, the modulus is highly dependent on the confining stress. As you confine sands, the modulus goes up a lot. So what's happening at the edge of my footing? Very low confining stress. So I have a constant applied stress, and even though I have more stress in the center as a function of depth, I'm going to get more settlement at the edges because in sands, I'm going to have a lower modulus at the edges. So this one I have a lower M at the edges, lower M or E, whichever way you want to say that. I hate it when you come on like that. Oh well, forget it. And here you're going to, this one you have a constant M or E, whichever way you want to say that. Okay, well what happens when I put a rigid footing? Oh, I have those pictures there for you. And I can see again that I gave you the wrong slides because everybody's got the white stuff this time, right? And you're happy about it? I know, I screwed up again. Well, what happens with, in the case where I got a rigid material, well, what happens to the rigid material? If I have a rigid footing, by definition, my settlement has to be constant across that footing, right? So now let's look at the contact stress. And this is the contact stress we would measure for a clay material under a rigid footing. Why do we no longer have a constant contact stress? Well, I'm still going to have the issue that the distribution of stress is going to go deeper under the center of the footing than the edges of the footing, right? So I'm going to be loading more material in the center than the edges. So what's the only way I can get a constant strain out of the material? Well, the only way I can do that is by reducing the load in the middle and shedding it out to the edges. Because the modulus is constant. So I know I have to have a constant settlement. Well, the only way I can do that is by taking load in the middle and pushing out to the edges. Because if the load that's in the middle, it's going to go down deeper based on stress distribution theories. And in sands, if we have a constant, because we don't have a constant modulus because we got lower modulus at the edges, how's the only way that I can get a uniform settlement if I have a lower modulus to the edges, well, it's just the opposite. I got to shed load from the edges and put it in the middle. So our contact stresses are not necessarily constant. And we more often, I don't say we more often, we often have this situation where we have applied loads that are very rigid, and we often have ones that aren't. But you're not going to get uniform stresses. If you have uniform settlements, you can't have uniform stresses. And if you have uniform stresses, you can't have uniform settlements in any material. All right. Well, so we don't have uniform stresses. What's the problem with all our models? Well, real soils, real footings on real soils, we got all kinds of issues. First of all, E is not a linear function with Z. It generally increases with depth, but it's not necessarily linear. And we could change materials. We could have step functions in it, right? Anybody who's looked at a CPT log knows that it's not a linear increase. Right? Well, the loads aren't generally applied at the surface. That was an assumption of all elastic solutions. Generally applied some distance below the surface, right? Many, many times we have a rigid material at the base of it. So our compressible layer doesn't go down forever, or if you're talking about an elastic solution, it suddenly hits a place where the modulus increases. This is the problem I thought that I'd asked you to look at in the settled 3D problem we did the first time, and I was so unclear in my problem statement, most of you didn't actually look at this issue. But the stress distribution doesn't follow a Boussinesq stress distribution now when you've got a stiff material under a more flexible material. And foundations have a finite stiffness. They're not infinitely flexible or infinitely stiff. And probably most important of all, soils aren't an elastic material. Although we did notice in monotonic loading that we can get an elastic type behavior in some cases. All right, so this leads us to what I like to call the generalized elastic method for computing settlements. So a bunch of people have done this. Many, many people have solved this problem. There's a whole list of a bunch of them. We're going to look just at two of them. We're going to look at Janbu et al. And we're going to look at this one, and we're going to look at this one. All of these have the same general form. All of them have the form that you take the applied stress times the footing width divided by the modulus, and then they all have a series of influence factors based on what's in their model. But they all have the same general form. It's Q times B divided by E, and then you've got some influence factors. Okay, so where Q is your average footing, B is the half width. Some of them are defined in little b, which I use little b for the half width and big B for the full width. They could be half width footing or could be full width footing. E is some kind of a soil modulus. Sometimes people are very clear on what the modulus is. Sometimes they're kind of sketchy on what the modulus is. Schmertmann's kind of sketchy on what the modulus is. And then I are influence factors that account for the size, the rigidity of the footing, the depth of the footing, the depth to a compressible layer, whatever's in the model. And I did say those are the only two we're going to cover. Okay, so let's talk about Janbu et al. And we say Janbu et al. 56. We actually mean Janbu plus Carrier and Christian 1978 because Carrier and Christian updated Janbu's influence factors, but they didn't think of the solution. So it's really Janbu's et al. Solution. But you need to do those two things together. This is a very, very simple method. It includes influence factor. It includes the most important influence factors, which have to do with the embedment depth and a finite thickness of the soil. And it also accounts for footing shape from square footings to infinitely long footings. So it's got all the most important stuff. This was originally developed, this is why I don't like this definition of instantaneous settlement. This was originally developed for the concept for distortion-only settlement, where Poisson's ratio is equal to 0.5. But if you put the right modulus, if you don't want to use a Poisson's ratio of 0.5, then just put in the ratio of the Poisson's ratio you want to use in here, and you can use it for any modulus setting you want. It has this form, where the settlement is equal to, we're using Janbu's notation, which is the same as your text, is equal to mu1 times mu0 QB over E. Mu0 is the embedment factor that has to do with how deep the footing is located. Mu1 includes both the finite thickness of the compressible layer and a shape factor. And you have these figures in your text. to do the computation. It's a very, very simple computation. We only have one value for the modulus now, though. We just have E for the modulus. So I'm going to ask you to, for one of the homeworks, to do the settlement calculations from that Mayne paper. It's a really nice case history, very simple, but really nice case history. And I'm going to ask you to compute the settlement based on this method along with two other methods to compare it. So you'll get a chance to exercise yourself with this method. So from there, so this is a very, very simple. This method's in all the books. Everybody shows this method, really, really simple, and works pretty well if your material can be described by a constant modulus, and you know what that is, it works just fine. Okay, so let's talk about this model. This is that model where we have not a constant modulus, but a modulus starts at a finite value and then increases linearly with depth. Mayne and Poulos developed a solution for this one that's working, that works very much like Christian and Carrier's model. They were working off of work that other people did, and they have influence factors that include both the embedment depth of the footing, the finite thickness of the compressible layer. It also includes foundation rigidity, so that you can deal with a foundation, like if you're doing a settlement for a mat that's got an intermediate rigidity. It's not a footing where it's really, really stiff, and it's not a tank where it's really, really flexible. You can actually account for the intermediate rigidity of the footing, and you'll get a chance to do that with the case history you're going to work on. And this is their equation. So now they just have three influence factors. They need three influence factors because they have three things they're going to take care of. And rather than just making this for an incompressible one, they have it as a function of the Poisson's ratio. These are the three influence factors. One factor for the finite thickness of the layer. One is a foundation rigidity factor, and the third one's an embedment factor. And they also are plotted so that you can account for footing shape. And for two of these, they have equations that you can use for the rigidity correction factor. They have an equation which you can use, and for the displacement influence factor, they call, which has to do with the thickness of the This is a ratio. This has to do with how thick the compressible layer is as a function of the rigidity. There's an equation, and one of these you've got to use. I may be confused now. One of these you have to use you plot for. The other ones you can use expressions for, and this is the embedment factor. So that one accounts. So what's the problem? What's the only problem with that one? Well, the only problem with this one is that we're still stuck with a linear model for the increase with depth. So this would work really well if you had a deep clay deposit that was normally consolidated. If you're in the Bay Area, you know that pretty much the modulus increased pretty linearly with depth. It would work in stuff like that, but it doesn't work in stuff where you've got a big increase in stiffness and it decreases. You got a material, there's jumps in it. But if you can model your material as a linear increasing function of depth, then you can use this method. Okay. So now the question is, well, what modulus should we use, and how elastic are soils anyway? Well, we know that the stress-strain behavior for soils, could look like that, could look like this. But let's look at the strain softening soil first in any case. Whatever the kind of soil we have, we're going to start off with some initial tangent modulus. This is also the seismic modulus. If you're measuring wave modulus based on wave propagations, you have very, very low strains, and this is the modulus that controls wave propagation. If we're really interested in what's going on at some point out here, well, I've got both the tangent modulus that I could define it at. This is the region of working stresses that I'm interested in. Or alternatively, I could define the stress-strain behavior at that point by the secant modulus. And those have advantages and disadvantages. The secant modulus, if I'm trying to understand if this is the range of stresses I think I'm going to be operating in, and I want to know what's happening when I go from 0 to there, well, the secant modulus is pretty handy because it's going to get me from 0 to that point. What's bad about the secant modulus? Well, if I'm interested in the loading at a different location, I'm going to need a different secant modulus, right? What's bad about the tangent modulus? Well, what's bad about the tangent modulus, if I want to get from 0 to there, what do I need to know about the tangent modulus? I need to know it all the way along the curve because I've got to basically integrate the displacement as a modulus changes. I've got to integrate the strain. So the secant modulus is really, really handy because I can pretend, if you want to think about it, I don't really think we're pretending that the soil's linear elastic. We're just saying this is an approximation to calculate the strains in a given region. So if I know the region in which we're working, and if I can get a secant modulus that gives me a pretty reasonable answer within that region, that's very, very easy. But it doesn't work in other regions. If I'm going with the tangent modulus method, well, I've got to know that tangent modulus all along the curve, or else I can't calculate displacement at some point. So I'm stuck with either knowing the tangent modulus all the way, which basically knowing the whole stress strain curve, or if I want to use these linear formula, I need to get a secant modulus that's appropriate for the level of stress that I'm working at. So when you apply any of these other models that we just looked at, whether it's Mayne Poulos' model or whether it's, oops, that's not the one I wanted to show. Or whether it's Janbu's model, which is a constant E with depth, whichever one of those it is, you need to get if you're going to use those, you need to get a tangent modulus that's appropriate for the stress level in which you're going to be working. Otherwise, it doesn't do you any good. So that's kind of the trick to the whole thing. Well, so how do we get these elastic moduli? Well, we can estimate our elastic properties for soils based on correlations. So if you look at Kohalwi and et al. Is a really good reference you guys should look at. That's the one for his EPRI. He and Kohalwi and Mayne and a bunch of other people put together a big reference for the Electrical Power Research Institute. And it's now in the public domain, so you can get it, and it's got correlations for all kinds of stuff. It's a really good reference to get. So here are some ways to estimate Poisson's ratio. Poisson ratio is not too bad to estimate, and you need to think about whether you're measuring things for drained or undrained conditions. Obviously, if you're looking at drained conditions and undrained conditions, you can have different moduli. So for saturated clays, we generally think they're incompressible, and we can use for undrained conditions a Poisson's ratio of 0.5, and here's some other Poisson's ratio which you can see are suitable. For sands under undrained loading conditions, here's an estimate of that you can use for Poisson's ratio. Elastic moduli for soils. For clays under undrained loading, this chart from Duncan and Buchignani is a very classic method for doing this. It's very common for us to correlate the secant modulus as some constant beta times the undrained shear strength. So this is where we're saying, well, if the soil's stronger, it's probably also stiffer. And then the work by Duncan and Buchignani shows you that that beta factor is a function of the over-consolidation ratio. And this plot is in your, this is in Holtz-Kovacs figure 13.6. He's kind of got this stress strain stuff spread out all over the text, which I find a little frustrating, but so I've been trying to give you the references for that. And you can use that to estimate the modulus. In sands in sands, we don't usually try and estimate the modulus based on any lab tests because it's pretty hard to get a sand out of the ground and get it to the lab and test it in any form that's going to be done. So usually we usually get modulus in sands either from correlations with CPT tests or by using the DMT test, which is actually a direct measure of displacement and of stress and strain. The dilatometer. Dilatometer is the one you push down in. It's got a little button that gets pushed out sideways into the soil. And that gives you a measure. That was the only, as far as I know, the only in situ test. Well, that and the pressure meter test. And the pressure meter test is really hard to interpret. But the dilatometer, I think, is the best available method for estimating moduli or measuring moduli for in situ soils. All the other measurements we do for in situ that we use to get moduli are all conversions from some kind of a strength test, like CPT or SPT, to modulus. And converting strength to modulus is not necessarily a good way to do it if you can measure it. So that's how you can get modulus. So with these semi-empirical methods, the weakest link is getting accurate estimates of the, the weakest link of these elastic models is, one, getting elastic properties from in situ the soil that works. So these work fairly well where you have relatively uniform soils and you've got some local correlation between measurements that you do in settlement. So if you've measured the settlement of a lot of mat foundations in Houston on Beaumont clay, and you've got measures of the SPT tests or CPTs in the Beaumont clay, and you can correlate those, then you can do a pretty good job of estimating elastic settlements or heave and foundations using these elastic models. And I use that example because you go down to Houston, and lots of times they do these deep excavations in the Beaumont clay, and they got to estimate the heave, and they do it this way all the time, and it works pretty well. Why? Because they've got good correlations between those elastic properties and the material. The solution, the alternative to that is some semi-empirical methods that combine elastic theory with field determinations and properties, and that's what we're going to cover next. And I was going to say, I think even though we're way past it, I think we need to take a break. So let's take a break because I've been talking for way too long. All right, so now we're going to look at some semi-empirical methods that combine elastic theory with some empiricism, and we're going to see how those work. So the first one is Schmertmann's method. So this is a very, very common method. How many people have actually used Schmertmann's method? But a lot of you have already used Schmertmann's method, right? Yeah, very common method to use. This is the basic equation. Again, notice it has the same form of the other equations we talked. The settlement's a function of Q times B divided by E, and then a whole bunch of influence factors. In Schmertmann's model, E comes from CPT tests. It's the correlations between the QC values, the tip resistance, and the modulus. So we're correlating a strength measurement with modulus, which isn't terrible, but strength isn't deformation. I epsilon is a strain influence factor. So remember when we're going to talk about this a little later, but your classic settlement that you did of a footing on a clay material, right? You use the stress distribution factor as a function of depth to calculate the settlement, right? You accounted for the change, the change in stress as a function of depth with the stress influence factor. You looked at the change in stresses down the center. Schmertmann replaces a stress distribution factor with a strain distribution factor, and we'll talk about that. And it's based on elastic theory, but modified empirically. C1 accounts for embedment. C2 is a creep factor. This is the only one of those that actually has a creep factor in it. And C3 is the shape factor. So here's how you get the modulus as a function of depth. If you're using Schmertmann's method, if you go back and read his 1970 paper, don't use the modulus correlations from that paper because they've been updated since then. You knew the ones from his 1978 paper, and then Robertson and Campanella did some more in 1989. So there's different solutions for this correlation, and this is a set that Professor Kudo consolidated from several references. Right. If we do the elastic solution for the strain, remember we all looked at a bunch of distributions of stress as a function of depth, right? This is not a distribution of stress as a function of depth, but strain as a function of depth for a circular footing or circular loaded area on a uniform elastic half space. And notice what's going on. What's interesting here? The maximum strain. Now, if I'd asked you before I put this up, where does the maximum strain on footing occur, what would you all have said? Immediately under footing where the stress was the highest. No, that's not the case. Why is that not the case? Now, this is for a frictionless mass, a frictionless circular loaded area on an elastic half space. So this doesn't have to do with confining stress of a rough footing or anything. This has to do with Poisson's effect. At the surface where the vertical stress is higher, the horizontal stresses are the highest too, and it tends to confine the soil, and you're going to get less distortion. And a little bit below the footing, in this case, half of a diameter of the footing below the footing, you're actually going to get your highest vertical strain. So that's the first thing Schmertmann observed is, hey, we're not getting the maximum strain right under the footing. It's like half a B below the footing. And you also notice this is a significant function, that the magnitude of the vertical strain is a function of the Poisson's ratio. But the point where it peaks isn't very strongly a function of that. And these are solutions. These are, so that last one was theoretical elastic solutions. These are from Schmertmann's 1970 paper. And these are finite element solutions for a rigid footing with perfectly frictional footing. In other words, there's right immediately under the footing, there's no lateral spreading because the footing's attached to the soil. Excuse me. And you notice we have the same. You have the same behavior, although the peak of the vertical stress is actually a little deeper under this case. So these are from finite element, and they also use a nonlinear stress strain curve in this finite element solution. So he's got elastic theory, and he's got some finite element solutions for some nonlinear materials that still show the same strain behavior, where immediately under the footing, the strain isn't the highest, it's actually higher some distance below the footing. So Schmertmann's idea is, instead of using stress distribution to account for the change in the strain, if you want to think of it as a function of depth below a finite size footing, I'm going to use a strain distribution factor. And his strain distribution factor is a very simplified one. We're engineers. We like things simple, so he made it a triangular distribution, very simple triangle instead of the ones that you saw, the curved ones you used to get from elastic theory. And so Schmertmann's method is now, so this accounts for both increased stiffness of the soil directly under the footing, and it also accounts for it also accounts for the friction of the footing on the surface. So this is just a quick visual caption of Schmertmann's method. If you've done this, it's slightly tedious, but with spreadsheets, it's not very tedious at all anymore. So we start off with our soil. We have a stress distribution. We have a CPT test of the soil, and we normally divide the soil up into layers where the tip resistance values are relatively constant. And then we'll go back to the ratio of QC over CP and calculate the modulus. So we'll go back to a table like this, and based on our soil type, if we had a young, normally consolidated clean sand, then the ratio of the soil modulus to QC is between 2.5 to 3, so we might say it was 3. And then we're going to come back to this figure. And so this is 40. This has got a QC of 40 kilograms per centimeter squared, so the soil modulus for this section, which is going to be E here, is going to be 40 times 3. Now, he called this a soil modulus. It doesn't include any Poisson's ratio. He called it the equivalent soil modulus, which presumably accounts for both the stiffness of the soil and whatever Poisson's ratio it had. And he did this by doing plate load tests. He did screw plate tests. He'd screw a plate down into the soil and then do a compression test on that plate at different depths, and that's how he estimated the modulus. So he's directly measuring the modulus, he's directly measuring the vertical displacement of a circular plate in the soil where he's done a cone penetration test. So whatever modulus he's getting is an empirical modulus based on field behavior. So he doesn't have any Poisson's ratio in there because he doesn't really know what it is and didn't bother to measure it. So it's an empirical E. And then you plot next to that your strain influence factor, and the actual shape of your strain influence factor, the magnitude of it and where it starts is going to be a function of the loading properties, and you can look that up in Schmertmann's method. And then now you know, so for any layer, so now we're going to divide this up into layers where the modulus is constant, and all you're going to do for each one of these layers, you're going to calculate the influence factor here, the middle of each layer, you know the modulus for each layer, And you can do this little summation right here. Oops, sorry, page up. And then you're going to have to calculate your shape factor, your creep factor, and your, actually this is the depth factor and this is your creep factor. I mean your shape factor. So it is a modulus-based method. Notice that it has the same form as our elastic models, right? It's Q times B divided by the modulus. Instead of using stress distribution, Schmertmann uses strain distribution. And it comes from this observation that the largest strain is not immediately under the footing, but at some distance below the footing. And his modulus values were based on field tests and are empirically derived. Okay, let's talk about the dilatometer for a minute, because this is a really nice device. So the dilatometer is a little, very thin stainless steel blade. This is, do I have the dimensions on here? Oh, good. So it has a little diaphragm that's going to get pushed out sideways into the soil. That diaphragm is 60 millimeters in diameter. The thing's not quite 100 millimeters wide, and the thickness is 14 millimeters. So it's quite thin. And you push this device into the ground, and then you pressurize the fluid behind the diaphragm, and you push it out. So this is what happens. It gets pushed into the ground, and you have a gas bottle in here, and you first measure the pressure required just to take that diaphragm. It's got a little contact where it's seated. And at first you measure just enough pressure that it comes off the seat. So and that's supposed to be some pressure related to K naught, if you want to think not K naught, but to the lateral earth pressure. And then you measure the pressure required for that button to deform 1.1 millimeters. So you get two measurements out of this, P0 and P1. And I think I assigned Marchetti's original paper to you guys, didn't I? I think so. I don't know if it's on a one-page summary one or not. I know I assigned the paper. So P0 is the pressure required just to keep the diaphragm seated. P1 is the pressure required for the diaphragm to move 1.1 millimeters. You measure delta P, which is P1 minus P0. And there's several properties that you can get based on these measurements. The first one is the material index property, which is equal to delta P divided by P0 minus U0. So this is supposed to be tell you something about the actual material. So if you've got low values of the index value, that indicates clay materials. And if you've got high values of the index property, that tends to indicate cohesionless materials. So this is kind of like Schmertmann's soil behavior type index from the CPT. There's a horizontal stress index, which is just equal to the seating value minus U0. So you want to think that's the effective horizontal stress measured by the dilatometer divided by the effective vertical stress. So that should be a measurement of the horizontal, that's kind of like a measurement of K, right? That's why it's called KD. So that's sort of like a lateral earth pressure coefficient measurement. Marchetti has a correlation between that and the overconsolidation ratio that's shown here, 0.5 kd raised to the 1.56 power. And these are all empirical. Both this table and this equation are empirical based on a significant amount of field data. So you can also get a modulus from the dilatometer because we're going to measure the stress required to get a certain displacement. The nice thing about this is now not a strength. This is the only test that's not a strength test. It's actually a deformation test. So from elastic theory, this should look familiar. This is just the elastic. This is the elastic settlement of a circular loaded area. Pushed. This is elastic half space, except we did it going vertically before. Now we've turned it on its side. It's the same equation. So this should look really familiar. It's 2 times B over P divided by pi times 1 minus nu squared over E. So this is the same equation as for the settlement of a circular loaded area on an infinite half space. So we can rearrange this to get the modulus terms on one side. Then we got that Young's modulus divided by 1 minus Poisson's ratio squared. is equal to 2b times delta p pi over the displacement. And then what Marchetti does, he defines ED as the dilatometer modulus. It's just E over 1 minus nu squared. And then B is always equal to 60 millimeters, and the displacement we always push it out is always 1.1 millimeters. So when you put those two numbers in it, you get that the modulus ED is equal to 34.7 times delta P. So that's all geometry. Be careful when you do this. Some of the early versions of the, when you read this stuff in literature, some of the early versions of the dilatometer had the displacement being 1 millimeter, not 1.1 millimeters, and it changes this number a little bit. So make sure when you read this stuff that you're using the right. This is sort of like the Schmertmann's thing. Don't look at the original QC versus E values from 1970. Look at the later ones and make sure you don't. I think at the very, I don't think I had you read the earliest paper from Marchetti, but his early papers, the earliest versions of this, they were using a 1 millimeter displacement instead of 1.1 millimeter displacement, and it makes a significant difference in this number. So this is not a Young's modulus, and it's not a constrained modulus. It's something in between, right? This is the modulus for the displacement of a circular loaded area on an infinite half space. So it's really not Young's modulus, or it's not constrained modulus. Just like that E sub s for Schmertmann is neither Young's modulus or the constrained modulus. Okay, so how do we convert that dilatometer modulus into that ED into the dilatometer modulus? So we're going to take this ED that we measured and multiply by this factor R sub m. And R sub n is going to be a function of soil type. So it's going to be a function of the overconsolidation ratio and the soil type. And you don't need to understand this stuff at this stage. You need to read his paper to do it. But there's all these values for Rm depending on what material you're in. So if you've got a high overconsolidation ratio, then you can measure very, very stiff soil in the horizontal direction, but the vertical displacement's going to, this vertical modulus is going to be different. So it's a function both of the soil type and of the overconsolidation ratio. And he's correlated all these things with field behavior, and that's where these values come from. If you read his paper, he'll talk to you theoretically about where these came from. And in general, just so you know, this correction factor or this R factor generally ranges from 1 to 3. Okay, so how do we predict settlement with a DMT? This is very simple now. So what we're going to do with the DMT is we're going to perform the DMT as a function of depth, and we're going to get this DMT constrained modulus as a function of depth. So we're just going to push that. You push this down. You push it about 30 centimeters. Push it down, make a measurement. Push it down, make a measurement. It doesn't go nearly as quick as a CPT because you got to stop and make measurements, and you don't get a continuous reading like you do as CPT. But you get a lot more data than you do, for instance, from like an SPT test. But you're only going to get measurements every so often. And you'll see examples of this from Mayne's paper that you've been assigned. So then we're going to then you look at the shape and size of the footing, and you're going to use a regular Boussinesq stress distribution to calculate the change in vertical stress, just like you've always done traditionally for a footing settlement. So we're going to go back to using stress distribution as a function of depth. So we have a modulus as a function of depth, and now we're going to have a change in stress as a function of depth. So now all we got to do is compute the settlement as the integral of the change in stress, which we know is a function of depth, and modulus is a function of depth, dz, which is really just going to turn into the summation of delta z over mz times the thickness of each layer. So we're going to have a, if we've got a square footing, and it's going to have a stress distribution. It starts off here at Q0. It's going to have this is B, and this is B, about 2B below the footing. This is going to be 0.1 times Q0. We're going to have a stress distribution that looks like that. And then from our dilatometer test, we're going to have M from the dilatometer as a function of depth, and it might look something like this. There might be a soft layer down here, but we're going to have these. We're going to divide this up into layers. Every place we got a dilatometer measurement. From the dilatometer measurement, we're going to get our M value. And from the stress distribution, we're going to get our change in vertical stress. And then we're going to know H sub I for each layer, and we'll just do this calculation. Very, very simple in concept. So this is actually the method that Schmertmann recommends now as the best way to calculate settlements for footings on sands, and I would concur with that conclusion. It's definitely not the most common one done because CPTs are a lot easier to do and a lot easier to get a lot more data for, so I think people are still using Schmertmann's method. But the trouble is, what's the weakest part of Schmertmann's method? The weakest part of Schmertmann's method is this table right here. You've got quite a range of QC to E values that you can use. Yeah.
You cannot use for the clay. No, none of them you can use it for clay.
Yeah. So the dilatometer you can use for the clay. Absolutely. Yeah. You could. That's another nice thing about the dilatometer. You can push it in anything and measure it, and that measurement is pretty. That measurement's pretty close to a drain measurement, just because the displacement's so small, and even with clays, the drainage distance is really, really short. So. Summary. So elastic solutions are good. They can provide good estimates for short-term settlements on saturated clays. They can provide good estimates for long-term settlement for stiffer over-consolidated clays, because those are the ones that when we looked at our stress strain curves were fairly linear, right, in the arithmetic space. And for settlements on sands, we can use these methods if we have a fairly constant modulus. So there's some circumstances if they work well, particularly if we have local knowledge of how to estimate the modulus based on, correlations between index properties or CPT or other measurements and the local behavior. So we've got good data. The difficult property is in determining these elastic properties. Don't forget that contact stress is not uniform. If you've got a flexible foundation, then by definition the contact stress is going to be uniform, but the settlement's not going to be uniform. If you've got a stiff foundation, the settlement's going to be uniform, but the contact stress won't be. These semi-empirical methods seem to be the most useful, particularly for settlements on sands, other materials that you can't get laboratory measurements for. Schmertmann's method with the CPT is very, very common and commonly used. Marchetti's method, or the incremental constrained modulus method, using Marchetti's data with the DMT is probably a better way to do it. So if you really need to know the settlement very accurately for some site, and you're really concerned about it, then see if you can't go get DMT tests. DMT tests can be run on any, most of the companies that do CPT will also do DMT for you, because they just screw a different thing on the end of the probe and push it down. It's a little more expensive and takes longer. I know that Robertson's company, what is it? Greg, thank you. Greg Drilling does it. You guys, other guys practicing guys know other people who do DMT? Greg does it all the time. It's more common in some areas than other areas. But it's a really useful method, very simple to do. All right? Questions? Since it's Marchetti Day, I can say questiones. All right. I will see you guys, not Tuesday because it's my day off, because it's Veterans Day, but I'll see you guys a week from today, right? And I'll definitely have your test graded by then. I was going to tell you I'd have them back to you on Tuesday, but I guess that doesn't matter.